Okay, thank you. Welcome everybody. Thank you for coming to our actually last seminar of the semester. It's a pleasure to have here Dr. Matthew Kahle from the Institute for Advanced Studies at Princeton University, or no, next to Princeton. You told me yesterday that it's not part of Princeton University, and I always associated it with Princeton University. At any rate, it's a pleasure to have here Dr. Kahle. Dr. Kahle completed his PhD in mathematics at the University of Washington in 2007. He's held fellowships at Stanford and IAS, where he's currently located. And he'll be starting as an assistant professor in the math department at Ohio State next fall. His research interests lie at the intersection of topology, geometry, probability, statistical mechanics, and combinatorics. He's actually had quite a few interesting and exciting contributions even at his young age, and it's a pleasure to have him here. Thank you. The floor is yours.
Thanks a lot for the invitation to come. It's been very nice visiting for the last day or two, and I've enjoyed all the conversations. So I want to tell you today about configuration spaces of hard disks. Since I've gotten this question once or twice by people maybe who just glanced at my webpage or CV, they thought maybe hard disks meant disk drive or something. And although I am a mathematician who's interested in applications, I don't really know anything about how hard disk drives work, and that's not what I'm going to be talking about. What we will be talking about is little point particles, like maybe the simplest model of matter that you can imagine. And I want to try to convince you that it's even the very simplest model of matter to try to understand it mathematically, whether through numerical simulations or through a theoretical approach. It's challenging, and there's a lot we have to learn about it. So maybe everyone in technical discipline of any kind has the experience of being at a party or being in some kind of social situation, and someone asks you what you do, and you say, I'm a mathematician, or I'm an electrical engineer, or something, and they say, oh, well, what do you do, though? What is your research about? And then you don't know what to say because you don't want to be boring at the party. So I sometimes say that I'm interested in how liquid turns to solid, basically. In our business, we would call it phase transitions, right? I think that's what most people here would probably call it. But that's I really think that we know that liquid turns to ice. That water turns to ice if you either get it to low enough temperature or high enough pressure. But I think there's actually still a lot of mysteries about why that is, why it's so universal across materials. So that's what I'll start by talking about. So the hard spheres model of matter, I think, one might argue that it's been around for a long time. Here's Leucippus, the ancient Greek, and he's considered the father of atomic theory, suggested that all of matter is made out of small, indivisible particles. It's a provocative idea. It's kind of interesting that someone just thought of that, right? It's not based on anything experimental, obviously, at that stage, of our human knowledge. But he sort of guesses right. So here's a typical phase portrait. This is what I'm talking about a little bit. Depending on the temperature and pressure, one has different states of matter. Okay. In the hard disks model, we really only have one parameter. It's sometimes called in the statistical mechanics world a thermal model of matter. So we've just got a bunch of non-overlapping spheres in some container, And you can either study the kinetics, where they're moving around, but actually, surprisingly, the theory of statics, even, where the particles aren't even moving, it's still pretty rich. So then what is allowed to change? What's allowed to change is that the amount of the volume of the box that the particles take up. And you can think of that as pressure. A solid liquid line that sort of extends to infinity seems to be pretty universal across materials. And Uhlenbeck, famous physicist, said since these are general phenomena, they must have general explanation. And the precise details shouldn't matter. Another comment sort of along these lines is that when one puts something at high pressure and makes it go through that liquid-solid phase transition, the basic idea that a lot of statistical physicists think about is that at that point the sort of the pressure or sort of the attractive forces, any attractive forces between the particles should not be important at this point. All that's important is their sort of repulsive force. In the hard disks model, if you actually write down an energy potential, which I don't think I have a slide for that, you could just imagine putting down spheres in three-dimensional space or disks in two-dimensional space and saying that the energy potential is 0 if they don't overlap or infinity if any pair does overlap. So in other words, everything is equally likely among the configurations that we're allowed to have. That's why they call it athermals, that there's no sort of Boltzmann constant. So Uhlenbeck suggested that at high pressure, the attractive forces don't play a role, and that the repulsive forces should be responsible. And thinking along those lines, John Kirkwood asked 70 years ago or more if a hard sphere's gas would actually exhibit a phase transition. So even in 2 dimensions, phase transition is observed in computer simulations. So here's, I'll show you a picture in a second. Once the disks take up more than some fraction of the total available area, the structure becomes much more lattice-like. So here's some random configurations at different densities. So this density at the bottom indicates what fraction of the total available area the disks are taking up. So at the bottom on the left, they're taking up about 48% of the available area, and things seem to be pretty haphazard. There's no apparent order to the disks, or very little order. And on the right, they're starting to organize themselves into fairly dense packing. So it turns out, just for comparison, that the densest packing of circles in the plane has been known for over 100 years. Well, it was proved mathematically 100 years, but I'm sure it's been known a lot longer than that. It's known to be the hexagonal lattice that you can see them starting to organize themselves into. And at that point, I think it's pi over root 12, about 90, 91% of the available area. So 72% is still pretty far away from that. But you can see that they're starting, many of the disks have 6 neighbors arranged at about 60-degree angles. So so one can measure this in various ways. So here's a function to measure orientational order. So we go over all n particles, and I guess this is just indicating that we can think of that as one vector in 2n-dimensional space, because we need 2 coordinates for each x. This is more the point of view we'll be taking in a minute, but it's not important for this calculation. So we look at e to the 6i. Theta j k is the angle between neighbors, between 2 neighbors of J and K are neighbors of some particle. And then, so the idea is if you're starting to get close to a hexagonal lattice, all these 6i theta j k's, because of that 6, now they're all going to be pointing in the same direction, all these vectors. And when you add up a whole bunch of vectors in the same direction and then average them, you get something that's very large. And if, on the other hand, there was no apparent pattern to the angles, then this number would be small. So it's just one-dimensional parameter. This is just one number. And if it's small, then we might say we don't measure bond orientational order. And if it's large, then we think something's happening. Another way to say this is you can correlate the angles at this disk with the angles happening at some other disk far away at this point. So what's interesting is that you can look at bond orientational order or translational order and different kinds of statistics people measure. Something seems to happen interesting with hard disks right around 70, 71%. They do simulations with millions and millions of disks. So as I was saying, just the statics here is interesting. It's a little interesting how they get a picture like this. It's actually, I believe, the first application of the Metropolis algorithm. So one starts with disks in an arbitrary pattern, presumably like a lattice-like situation, and then one repeats the following algorithm. Pick one disk up and try to perturb it randomly in a small little neighborhood. And if it overlaps with another disk or goes out of bounds, if you have a bounded region, sometimes they do this on a torus. But if it overlaps with another disk, then don't accept the move. And if it doesn't overlap, then accept the move. And if you do this for long enough, then the disks are sort of considered to be mixed up. Yes?
This slide, how do you define neighbors, the disks which are in contact?
Yeah, good, thanks. This is a good question. Because the disks are not in contact. So there's a couple different ways that people define the neighbors when they're trying to measure this numerically. One way is just look at the centers of the disks as points and take a Voronoi cells with respect to that, and then the sides of the Voronoi cells tells you. That's one way. The most recent simulations that I read about, they said it was faster to just say that you're going to have 6 neighbors and just pick the 6 nearest neighbors for each guy. Right, that's something I wondered about for a while, and then finally realized that there was different people measure neighbors in different ways. And there's variations on this theme. This formula isn't meant to be anything other than just one example of many different kinds of statistics that you could measure. Okay, so we want to look at the space of all allowable configurations. So if I have n disks, then I can think of this as a sort of a 2n dimensional space. But I have 2 parameters, n and r. So each one of these xi's has got 2 coordinates. And this over here, I was just writing the x. Yeah, so maybe actually that should have been a 2 in there. But each of these guys is between r and 1 minus r means that you're actually staying inside the square, and distance between them is at least 2r, because you need 2 radiuses between 2 centers of the disks. So this thing naturally sits inside 2n dimensional space, and so it inherits a measure. In other words, we can measure volume of subsets of this space, and it also has a topology from Euclidean space. And we'll mostly be talking about the topology today. But the measure is measure theoretic questions are sort of what's mostly been studied so far, what people have thought about. But to just give a good formula for how, fix n, to be some really huge number, and then let the radius vary. All we really know is that when r is very small, you have almost full measure, that you could almost put the particles anywhere in the box. And if R is very large, you have almost no measure. But exactly, the asymptotics of that is a very subtle question. And Giancarlo Roda said if we knew what the measure was, if we had good formulas for that, we would know why water boils at 100 degrees on the basis of purely atomic calculations. I mean, so one could imagine that there's actually a phase transition just in the measure of this space, that as the radius gets large, the radius of the disk, there's much less possible arrangement for them to sit in. And so that's why they're forcing themselves into lattice-like configurations. But nobody's ever really been able to give a convincing argument of that mathematically. Actually, I gave this talk at the Institute, and one of the mathematicians in the audience laughed at this. But he said, no, we know why water boils at 100 degrees. That's actually the definition of 100 degrees. We don't have to do this calculation for that. But this is a good point. I still like Roda's quote, but so one of my mentors at Stanford was Percy Diaconis. By the way, just it's sort of tangential, but his interest in this was in that Markov chain that I was telling you about. Pick up a disk and move it. And I said, well, if you do that long enough, then it's sort of mixed up, and you've picked a random point in this configuration space. But he's sort of one of the world's experts on mixing time of Markov chains, right? And so he wanted to make that mathematically precise and put bounds on the mixing time. And it's actually a very interesting story, but it's a story for another day. And he suggested looking at the topology. And in a very nice survey article he had in the AMS Bulletin, it's a survey article on Markov chain Monte Carlo. He said, we know very little about the topology of these spaces. For example, if you make R small enough, surely it's connected. You could get from any configuration to any other configuration. But how small do you have to make it before that's true? And that's just sort of like the most basic topological feature we could ask about, right, is whether it's connected or not. That's already a very subtle question. So, so this was a project I did when I was still at Stanford with my other mentor there, Gunnar Carlson, and an undergraduate researcher, Jackson Gorham. We were inspired to study this question by Percy, and then Gunnar pointed me to some computational techniques that might be useful. And Jackson Gorham, we were able to pay him for a summer to sort of write some MATLAB code and so on. So, so we want to look at the set of path components, I could just say connected components of this configuration space, and how it changes as R varies. And so what we're going to try to reconstruct is this thing called a dendrogram, which I won't try to define, but I'll just show you a picture by the end. And not only do we want to know, say, how many different components there are, but the persistent path components, and this is a whole world now in the applied topology. Gunnar Carlson is one of the experts on persistent homology. But basically here, we're just looking at connected components. We want to know not just at each radius how many there are, but sort of the structure of how they connect to each other and how new components appear. So that's a little bit more information than just the path components themselves. The structure, not just at any fixed R, but as R varies, what happens. So we'll do a sort of Morse theoretic approach. If you don't know what Morse theory is, that's fine. I think it'll just sort of, hopefully you'll get a flavor for it just from the context, what we're talking about. So first of all, just to suggest the Morse theory approach, so config in, now without the R, let's just say it's just indistinct points in the open unit square. By the way, we could do other regions besides the square. Again, it's just sort of a convenient example. And we found the square was complicated enough because of its corners and so on to actually give sort of a rich structure here, but simple enough that it's easy to program and that we could actually cook up interesting examples with. So, so we'll mostly talk about the square. So now I can put a function on that space by saying the min distance between a pair of those points divided by 2, or the distance to the boundary. So in other words, if I just put down n points, this function tells me what's the biggest radius disk I could put in, right? So then the hard disk configuration spaces are the super level sets of that. I could say config nr is the set of things in config n that go to something r or larger. But you can always shrink the disks. Once you've got them in a location, you're allowed to shrink them. So Morse theory is sort of a way of studying a space by studying its the sub-level sets of a function, or the super-level sets of a function. And here, actually, the nice thing is, to mathematicians, config n, the space of indistinct points in the unit square, is something that's very well studied topologically and geometrically. That's a space we already know a lot about. And so now we might hope that we could understand just a piece of that space at a time by filtering it by this function. The problem, though, is that normal Morse theory, that your function is smooth. At least this is the most classical form of Morse theory due to Morse. You have a smooth function. The thing is, these distance functions, those are smooth, but now you take the min of some, n squared of them or so, and it's not quite smooth anymore. But it's still pretty good. It's smooth almost everywhere, and it's continuous everywhere. So, but for our numerical purposes, it's convenient to actually just sort of substitute a smooth function for this min thing. So we'll just look at the distance between a pair of points to some huge power, and distance to the boundary to some huge power. And so if 2 points are close, then when I take 1 over that, it's some huge number. And then when I raise it to the huge power, then that one term dominates all the other terms. So you're really getting penalized by whatever pair of points is closest. So this sort of should capture the same things as minimum. So for the calculations that I'm going to show you, we set h to be something like 50. So MATLAB is dealing with some huge, 100, 200 digit, numbers. Well, I'm sure it's not carrying that level of numerical accuracy, but it's dealing with 10 to the 50, 10 to the 100 regularly. So let me show you that. So the first thing we do is to find local minimums of this function. And the way we do it is just to take 5 random points in the square. Oh yeah, so from now on in this section of the talk, n is 5, and we'll see sort of a rich structure even with 5 disks as the radius varies. So I'll show you a movie with more than 5. So here the hardness parameter in this first movie is 6 or 8 or something sort of. It's still somewhat hard, but somewhat reasonably soft. And I just picked, I think, about 50 points in the square and just flowed along, did a steepest descent, along the gradient of this smooth energy function. So that's a local min of that function. So here's what it looks like when you set the hardness parameter up to about 50. It's fun to think about why they jiggle around a lot more, why it's much more jumpy. I mean, I guess it makes sense that since the function's so much more steep, right? Or another way to think of it is that at any given time, you're really probably getting penalized for one of the smallest distances, so it's really only moves one disk at a time, almost always, and so it just sort of wiggles around, and it takes it a while. So that's what it looks like. I think it's still even moving a little bit at the end there. The number of disks is fixed. So we just pick a set of points of that number and then flow along. And so that gives us a local energy minimum. And we should think of that as where a component appears. Because these disks are locally as densely packed as possible. You can't put another disk down in there. And you can't even move them around and make them bigger continuously, at a certain point. So that's, if you're shrinking the disks from big to small, and at first there's nothing because the disks are too big to fit in the square, but then all of a sudden something like this, a component appears. So this is the first thing, is to see what are the local minimums.
Selected number of initial components.
The initial number of disks? Well, it'll depend a lot. So now I'll show you an example with 5 disks. Yes, is there a question or comment?
Maybe you should actually go address this question first.
Okay.
And then.
So, so here's what it looks like when we did this 10,000 times or more with 5 points. Every time it flows to a local energy min of this function, we get one of these situations. So these are, we think, are the only types of local minimums that you'll see with 5 disks. Now, if you got into 100 disks, you would see many, many different kinds of configurations combinatorially. So even with 5 disks, we're simplifying things quite a lot here. What do I mean types of local minimum? I mean loosely that if I flow, I end up in one of these configurations. But what does that mean? The 5 points are labeled, so they're distinct from each other. So really, the 5 points could be any of the permutations of these. So that gives you 120 times each of these. And then also there's the symmetries of the square to take into account. And these all have reflectional symmetry, but these don't have rotational symmetry. So these could be in any of the 4 corners. So, so there's, when you're, this is something that we have to sort of sort our data by that. We start with 5 uniform random points independently in the square and just flow along the the energy gradient with the energy function, that smooth thing that I just described. And these are the local minimums we find. So if you know Morse theory, these are our sort of index 0 critical points. This is where components appear as we're shrinking the radius. By the way, I found when I was doing this research that there's a huge literature on disk packing in finite regions. I mean, 2A solved the problem of density packing of circles in the plane 100 years ago, but if you want to pack circles in a triangle, square, or circle or something, it's, of course, much harder because it depends on what's the shape and how many disks you put in.
Stuff?
Yeah.
So what are...
So one special type of local minimum that we should see here is the densest possible packing. But so this turns out to be the densest packing of 5 circles in a square. If you've got 5 disks that are all the same size and you want to put them in as small a square as possible, this is it. And we had also found this one by hand, but I was really delighted when the computer program found this for us because we didn't know about that. So these are Conley and Sloan. I mean, if you don't know, they wrote a huge tome. Their book on sphere packings and lattices is considered not only the main reference for that subject, but it's considered one of the best survey type books ever written in mathematics. It's very celebrated, and even though it's maybe 20 years old now, it's still kind of the reference for researchers in sphere packings. But often the question that it seems like they're concerned with in many different situations is what's the densest packing? And so here, we're not looking for globally densest things. Just this part of finding index 0 critical points is just trying to find locally densest things. So here, I can't move those disks continuously and increase their radius at the same time. I can't even move them continuously and keep the radius the same. And even slightly stronger statement is you could shrink the radius just very, very slightly, and they could wiggle in place, but they couldn't get out of the corner. It's a pretty small amount that they could shrink by, but one can figure it out. So here's what the local energy minimums are. And so these are sort of where components appear. But if you want to understand the structure of what's connected to what, you need to go one dimension higher. You need to know not only what's the zero-dimensional part, but what's the one-dimensional part. So we need to find low-energy paths between these. What was your question or your comment?
Whether the way how you ran the simulation, the video, if it relates to how when we try to create a crystal in many systems, we kind of try to cool it. So we put some original, some crystal that we already have in the middle, and then we just cool it, and a crystal forms. But that's different from a diamond, which has like the densest packing, and a diamond was cooled, with immense pressure over a great period of time. So can you relate this to your simulations?
So it's interesting. So what I was doing was just what we thought of first, which was to just flow along the gradient of this function. That's a smooth approximation to the function that really defines hard disks. But then, as I was mentioning a minute ago, I started reading the literature about disk packings in different regions. And so you can find these beautiful tables by Ron Graham, among other people, where they say, well, what's the smallest square that I can put 36 disks in, 37, 38? And they go all the way up to 100 disks. And the way they do it is they're really looking for the densest packing. And what they do is actually somewhat similar in spirit to what we were already doing here, except they actually give the disk some initial velocity. So they put them down randomly and let them move, which seems like maybe having something hot, a solution, and then cooling it. And they have them bounce around with perfectly elastic collisions while they're growing. But they also do some sort of simulated annealing things to try to, to get the very densest packing. You might want to heat it up, then cool it back down. It's like, annealing, of course, comes from metallurgy and so on, but it's widely applied in Markov chain, Metropolis kinds of algorithms. So simulated annealing here would be to go briefly to shrink the disk again and then let them move around and see if they get into a densest packing. So it does seem to have physical meaning in a way, this sort of approach. But let me tell you about the next step, because I think this is interesting. How do we find low energy paths between these? So in other words, how much do I have to shrink the disks by in order to get between components that look like this? And then that'll start to tell us what the structure of components looks like. So the nudged elastic band method is due to theoretical chemists. So what we're going to do is we're going to start with a straight line path between 2 points. And in this case, it's going to be this one and then the same thing, but with this guy in the corner. Start with a straight line path, and then you approximate that with a polygonal segment. And then you try to flow along the energy gradient. But if you have a path that ends at 2 local energy minimums, and you just flow each point of that path along the gradient, it's just going to pull the path apart. So what the theoretical chemist said you can do is just make those little pieces of the path springs. So there's an extra force there that's orthogonal. And you can make it orthogonal, and so that you don't pull yourself apart. And so hopefully what happens, you can almost think of it as an elastic band that's pulling down and it catches on something. And so this could be, you could think of that as a saddle point. And that's what they're trying to find, is sort of semi-stable equilibria. So not just a local energy minimum, those are easy to find because those are actually stable equilibria, but there's a lot of interest in chemistry and physics of semi-stable equilibria. So here's what it looks like. I'll give 2 examples of this. And I have it change color when it gets to the maximum energy along the path, which means here the minimum radius. So the interesting thing is this is actually also an interesting configuration of disks itself. This is a jammed configuration in the sense that no single disk can move. Collectively, they can move because you see how they sort of rotated, how they slide into this. But in the jammed hard particle packing sort of world, like Sal Turcato at Princeton and some physicists and chemists work on this, the sort of abstract side of physics and chemistry of jammed hard particles. They distinguish between locally jammed and collectively jammed. So I would say, as a mathematician, that this is something like an index 1 critical point. There's sort of 1 degree of freedom. It's a saddle point in most directions. This thing is a local energy minimum, but there's one direction, one dimension in which it's a maximum. Yeah?
Normally in physics, when you're modeling phase transition regions, are those the phase transition points? Are those points modeled as globally jammed or locally jammed?
I'm not sure either. So we're taking a step back and just trying to say, instead of trying to understand the phase transition, try to understand the changes in the topology in general. And then maybe if we understand the changes in topology in general well enough, we'll start to understand the phase transitions. I guess that's, to me, the one possible long-term program. Yeah. Yeah, let me show you one other movie, and then I'll go back to the slides. So here's a little bit more interesting configuration. It sort of gets a little bit wonky at one end. And there's how you get from the X to the Pentagon. But let's go back to where, and it turns out, so they're not quite touching there in the middle, but one can sit down with pencil and paper and just say, oh, there is actually a configuration of 5 disks where they're touching exactly. I'll show you a picture of it in a minute. So this seems to be the smallest radius, the largest you can make your smallest radius to get from the sort of X configuration to the Pentagon configuration. So let me go back to the slides. And now, did you have a question? Would that go back one slide?
Yeah, like this one. I just want to know, when you do the simulation, what is the probability for each of these configurations to show
Right,
up?
I don't remember exactly. This one on the left is the most common, and this is the least common. This still happens 1 or 2% of the time.
Actually, if you increase the number of disks here, and you will get many configurations, right? Do you ever observe the spectrum of the probability to show up?
No, and that's a really interesting question. I expect as you just get slightly more disks here that there will be some local minimums that you will never see because they're at the tail of that distribution, right? It should fall off pretty fast. But just you could still do this numerical experiment with those configurations that you do see. It's a perfectly reasonable question. Try it with 10 disks or 12 disks. And just record all the different combinatorial types, all the different kind of tangency graphs that one gets. See, I'll show you a little bit more elaborate calculation in a second.
That your smooth version of your original nonlinear function is indeed Morse, right? And then it seems to me that you're going to have to run an awful lot of realizations for you to actually hit, because these extrema are, in Morse theory, they have to be isolated, right? So to actually hit that extremum, you're going to have a large number of experiments.
Right. Well, to find the index 0 critical points, though, those are energy minimums. So I could just take random points on the manifold and just flow, and I hit these. So there's a big basin of attraction. And then the idea of this nudged elastic band thing is to find index 1 critical points. And there I have at least index 0 ones to start with, and so I can go up. I'll tell you in a minute about an experiment that one of my friends did recently with finding higher index critical points on one of these. So here's the index 1. I think, no, this one I showed you. Oh, I'm sorry, this slide is outdated. This is supposed to be that funny-looking configuration. When I changed this talk over, this wrong slide ended up here. But the one that the second movie I showed you. So hopefully this part is right. Yeah. So so here's the dendrogram. So the x-axis is recording the radius of the disk, or really 1 over the radius. So to the left of this, 1 over the radius is too big, and the disks don't fit in. So right there at that line, that's the largest radius where the disks fit. Now as we go left to right, we're shrinking the disk to see what happens. That 120 is recording the number of path components. 120, of course, is just 5 factorial. So then the next thing that happens is once we get to this radius, about 5.1, those come in. And there's 480 because it's 5 factorial times the 4 corners that could be in. So now we have a total of 600 components, and they're just, as we shrink the radius, they can wiggle in place, but they can't get to each other yet. So then the first interesting thing that happens is these come in, and now these can slide around the edge to that. And I'll show you a picture in a minute of why this collapses down to 24 components. But you only have limited motion. You can slide them around, but you can't switch a pair of disks or something. So you get down to 24 components here. This is where we're sort of doing some combinatorics on the side. And then this thing comes in that I showed you in that movie. And we're down to 1 component. So now it's connected for this range of radius. And we might think that's all that happens. But it's not, because then these strange sort of high energy stable ones come in, I guess you could say, or very sparse, but still jammed configurations. And they don't last long, but they're there. So we see a number. So this is just the structure of how the number of path components changes as the radius varies. For 5 disks, it's already a fairly rich structure. For example, the number of components is not monotone. It's not even unimodal. It goes up, then down, then up, then down, the number of components as you vary the radius. And even path connectedness is not a monotone property. So a mathematician might foolishly conjecture that if it's connected, the configuration space, and you shrink the disks, it's still connected. No, because if you increase the radius of these disks, you're back in here, and it's connected, right? So this is just it's a toy example with 5 disks, but just to show there's many places where the topology changes. This is not even half of it with 5 disks, by the way. But just even if you only looked at what's connected to what, look at that level of topology. It might change a number of times and in really strange ways. So let me show you a close-up of these 24 components. So you can see, moving from one to the next is a slide that you're allowed to make. You can almost follow around the disk. And now I'm coloring the disk so you can keep track. And you see where the 20 comes from is because there's 5 different colors of disks and 4 different corners that they can go through. So it's a 20 cycle, and so 480 divided by 20 is that 24. So presumably right here, right at this change of the topology, those 24 components each have the homotopy type of an actual circle. For some brief interval.
Am I mistaken in thinking that that whole thing rotates as a one body? That whole set of circles as you go around the. Is that true or not?
Yeah, there's lots of symmetry in this picture. We could rotate the 5 colors or rotate the square and then rotate the circle and get the same picture back.
In your dendrogram, what's the difference between the vertical and horizontal rectangles? Is there any significance? Or?
Yeah, the vertical rectangle, the height of the rectangle is just indicating how many components. So when it's very skinny, there's only 1. And then, that 480 is to scale with the 120 and 24. The width is, of course, the radius when that change in the topology happens. So I'm just putting this to indicate the change that happens on that left side of that rectangle, and this to indicate, just with one icon, the change that happens here is marked by the existence of this kind of jammed configuration. So one of the take-home parts of this talk is really that these jammed configurations of disks act as markers for when the topology changes. Those are acting as critical points of a Morse function. And if people only take one thing away from this talk, it might be that jammed configurations of hard particles act in a very analogous way to critical points of a Morse function. So and to mathematicians, critical points of a Morse function mark the only places where the topology can change. So here's a few more computational questions. Higher dimensional analogs of the nudged elastic band to find higher index critical points. Or if somehow you've gotten a critical point just with pencil and paper, can you actually compute its index? So let me show you some experiments with 7 disks in a disk by my colleague Jeremy Mason, who's another postdoc at IAS. He's across the hall from me, and he's a material scientist who's been doing simulations of grain growth, and occasionally I distract him with some nonsense that I'm wondering about. Yeah, well, index 0, I would say, are the stable ones, and any higher index is semi-stable. So here's how he did it. He still uses that smooth function that we wrote down, but then he says, I'll just symbolically compute all its derivatives and sum their squares, and I'll try to find zeros of that. So now he actually does something tricky numerically. He finds, he does steepest descent, and then I'm not sure exactly what he does once he starts to get closer to the 0. It's more complicated. So let me show you all the different kinds of critical points he finds for 7 disks numerically. This is a local min, and so is that. Those are index 0. Oh, by the way, when he does this numerically, once he finds the point, he can go back in and find its Hessian and the number of positive eigenvalues. Negative eigenvalues. He can just figure out what the index is, also numerically. So here's an index 1 point. I'm going to flip through these because they're just to show you the variety. Some index 2 points, index 3, index 4, and there's actually one that we know about that he didn't find this way, which was index 5, which is all the disks going across in a row. But with this kind of just looking for zeros of the derivative of that function that we started out in some numerical trickery, we were able to find lots of different critical points of higher index. So let's see what, inspired by this sort of thing, Yuli Baryshnikov and Peter Bubenik and I have been trying to prove things. I've also been working this whole year with Bob McPherson about things that I won't be able to tell you about today for lack of time. But the main idea is you can actually do Morse theory even when you don't have a smooth function. And also we use some fact of Robert Kahle, who's a mathematician at Cornell and is maybe the world's expert on kind of combinatorial rigidity. Done a number of kind of amazing things in the world of rigidity of disk packings and so on. So using these kinds of ideas, we can actually sit down. Everything I showed you so far was kind of numerical experiments that are, I think, strongly suggestive, but we can prove some things, which is one of the things we care about doing as mathematicians. So here's 3 disks. Can actually sit down and characterize every radius at which the topology changes, and it's a fairly complicated calculation, even for 3 disks. So here's the first place. That's the densest packing of 3 disks in a square. If the radius is bigger than that, bigger than 0.25433, I'm writing these numbers down just for convenience, but of course it's really something we can write down exactly, an algebraic thing. It's square root of something plus square root of something. It's something awful number, but it's about that. And we know if the radius is bigger than that, they don't fit. And then at that point, then you keep shrinking the radius as we go left to right or as we go down this page. They can just wiggle in place. So there's 3 factorial times 4 corners, so there's just 24 components, and none of them have any topology. And then once they're small enough here, now they can start to move, and that top right corner can move down, but then we can just keep sliding them around. It's like the 15 puzzle, and so then we get 2 circles. Because you still can't switch 2 disks that are next to each other, but you can just keep moving them around. So there's one circle where they're oriented 1, 2, 3, and one where they're oriented 1, 3, 2. And then they're small enough that this disk can pass through, and that's when it becomes connected. And there's a calculation here, but it turns out that it's got the homotopy type of a wedge of 13 circles at that point. And then here is the last time the topology changes. And what I mean by classical homotopy type is now those disks are acting as points for that or any smaller radius. 3 points in the plane, it actually has a pretty interesting topology. It's not a trivial topology at all because we're insisting that the points be distinct. So they can't, so that makes a space that's got some holes in it, but we know what all the holes are in higher dimensions and so on, the configuration space of points. So now, so there's an example. So, but with 4 disks, we expect, these are the critical points that we found by hand, and the calculation starts to get really hairy. And I think we still might be missing one here. And then 5 disks, it's starting to get really ugly. So this is the number of places I think the topology changes, something like 20 times at least. And I'm sure at this point that we're missing critical points. Jeremy, I showed you the picture of 7 disks in a disk. He actually redid this calculation also. He did 5 disks in a square, and I think he actually found all of them that I had found by hand and found 1 or 2 more. And I can't remember if I've updated this to include the 1 or 2 more. And I've sort of got this like organized by index. That's definitely the last time the topology changes. I'll say more about that in a second. And some of these you've seen before. These are index 0, and that was index 1, and so was that, and so was that. And some of these others I'm guessing what the index is, and some of them I know. But so again, the take home is every one of these represents a place where the topology changes. It represents a singular point in the configuration space. So the idea is, I think when you have a lot of disks, which is what we really care about in the thermodynamic limit, there's many, many singular points, and maybe so many that some of that is actually going to capture something interesting statistical mechanically. But so far the theorems we have are sort of very simple compared to what we might expect is true. So this is just a statement that Yuli and Peter and I wrote down, that if you have n disks in a square, that the last time the radius the topology changes as you shrink them is when the radius is 1 over 2n. And so for 5 disks, it's this. And if you had n disks, it's when n disks fit in a row along one side of the square. And it's a more general statement than that. It works for different size shapes and higher dimensions and so on. But it takes some work to prove this. Unfortunately, this is very far away from the statistical, mechanical, and the thermodynamic limit, right? If you've got n disks, all this is saying is that if the disks only take up length and not area, then nothing's happening topologically at that point. But would be interesting is to make asymptotic statements as we get into the thermodynamic limit. But the nice thing about sitting down and carefully proving this theorem is it actually allows us to prove that the only places where the topology changes is when we have some kind of rigid packing of disks. Just defining the index of a critical point is an interesting problem in min-type Morse theory. So just to summarize, we can use Morse theory, both kind of computationally, actually numerically implement it in a few different ways, with the nudged elastic band method to find index 1 critical points, or at least with small numbers of disks, we can even just symbolically get all the derivatives of the gradient and just try to find zeros of that. And so we can find critical points this way. And then theoretically, we can justify that those critical points should look like jammed configurations. Those should tell us where the topology changes. Topology can be very complicated even for a few disks. And as I've been saying, the critical points of the Morse functions, that meaning places where the topology changes, correspond to these rigid configurations. So here's just an example of how little we know, though. What's the real threshold for connectivity? There is some radius such that for disks smaller than that radius, the configuration space is connected, but it's not known. And I actually wrote one paper sort of about this and suggesting that it's very small. Even when the disks only take up length and not area, if it's enough length that they take up, that the space is not connected. That's certainly true for a circle, by the way. You can just put them all around the boundary of a circle, and they can't get out, right, if they're the right radius. But for squares or for other size regions, or for, say, a torus, a boundaryless region, this is a wide open math question. It's surprising to me how little is known about this. This is a question that I've thought about a little bit, and I think is fun, is what about more metric questions on this? I guess part of the question came from looking at paths between these local energy minimums. So just imagine that you've got a configuration that's densely packed, and the disks can't move. And now you just delete a couple disks or shrink the radius just a little bit, so now they can wiggle around, and you want to get to a different configuration, like by, say, that you could have the same configuration but with the disks permuted, or you just want to switch this disk and this disk at opposite ends. Well, if they're very densely packed, you might expect you really have to wiggle those disks a lot because it's so densely packed. It's not easy to get from one configuration to another. And so the diameter of the configuration space might look to be very large when the radius is large, and it's very small when the radius is small because you can almost go in a straight line. The points might get close to each other and you just kind of barely bend to go around them. So I think so my picture of what this configuration space starts to look like when you're getting close to close packing density is that it's getting very small. That's the measure theoretic statement, but also that it's very complicated topologically, and you have these long tendrils. Maybe it might be hard to get from one to another. So diameter is just one parameter, but that might, if the space is disconnected, you could still talk about the diameter of its components that might capture some of the sort of wiggliness of the space or how complex it is. Of course, what we'd really like to know about is statements about how large are the Betti numbers and so on as the number of components goes to infinity. And the dream is to explain phase transitions topologically. I should say this is what I've been working on, various aspects of this project for the last couple of years. And then I finally recently came across a body of work in the statistical mechanical literature on the topological hypothesis in statistical mechanics, which is that underlying phase transitions are changes in the topology of the configuration space. And for example, there's a theorem in that literature that if you have a smooth finite range confining energy potential, that changes in the topology are necessary for a phase transition. So as the number of particles is going to infinity, if there's a phase transition in the Helmholtz free energy, then there are necessarily changes in the topology of those finite configuration spaces that are piling up at that change in the phase transition in the free energy. So in some cases it's proved. Unfortunately, that theorem doesn't apply to our energy potentials because for hard disks they're not smooth. But it does apply to those kind of smooth versions of hard disks that we showed. So it seems to me that this is part of the reason to look at these sorts of things. We can see that the topology is very rich. So maybe in these cases, the topology really can capture something about the phase transitions. So I'll just end with some acknowledgements, especially thanks to Stanford and supporting me as a postdoc, and for Percy for being so generous with his ideas. Gunnar Carlson also. So I think I'll end there. Thanks a lot.
So I sometimes get confused about several points about most things. So when we computed these different regions of R and saw the topology in those regions, can we put together all of this and tell what the topology would be for the whole configuration space or all R's?
Yes, and that's actually what the last. You're talking about that picture I had with 3 disks. Yes, so for thanks. This is actually something I didn't explain. The configuration space of in R is included in the configuration space in R prime if R is less than R prime. R prime is less than R, right? I mean, I can always shrink the disks. So as I'm shrinking the disks, I'm making the configuration space bigger and bigger, right? And so these sit inside each other as a nested sequence of spaces. This is the empty space, and down here, it's the whole configuration space. So the thing is, though, I would have to shrink the points all the way down to 0 to actually get the whole configuration space. But the point is that I only have to shrink them down to 1/6. I only have to shrink them down that much to get the whole configuration space up to homotopy type. So then they're acting like points as far as anything you could measure topologically, classically. You know, any homotopy groups or homology groups, which are the kind of things we usually use to classify spaces and so on. Those will all be the same from here on. So nothing interesting changes in the topology from that point. But yeah, these spaces do sit inside of each other. Yeah.
So would that be equal to the number of degrees of freedom of motion of this hard disk at that point?
I think that something like that is actually reasonable, and those are the sorts of things I've been thinking about. You want to be a little bit careful when you say degrees of motion. So you probably, the question is, do you want to look at degrees of motion where the
degree of motion.
what is that? Yeah.
Right.
Great. So that actually works pretty well here. I think it gets more complicated with more disks, I guess would be the short answer. But I think that should actually give us everything we want here. So here there's 0 degrees of freedom, it turns out. So we have to be careful what we mean. Yeah, so here they can't move at all without shrinking the radius. So let's keep the radius the same and see how much they can move. Here, well, let's ignore this one since he's not part of the critical part. So we'll just look at the critical part. So that's another subtlety already here to deal with. But it looks like 2 degrees of freedom. So, but actually we really only want this to be an index 1 critical point. So maybe another way to see this is here. This whole thing is critical as you move them up and down. So it's sort of like Moore spot theory. You have a whole critical submanifold here and not an isolated critical point. So there's one dimension of freedom of just moving that whole row of disks up and down. So let's subtract that. And then we can also say then each disk has 1 degree of freedom where it can move up and down. And locally they can't. So then 3 minus 1 gives us 2. And that's an index 2 critical point. So that seems to sort of work there. And then here, you know, well, we really only look at those 2 because they're part of the critical one. And we got 2, but they could also slide this way and still be critical. So subtract that, and now we're down to 1, which is the right answer. Here, you just count degrees of freedom, and you get the right thing, 1, because only that guy can move, and only in 1 dimension. But you already see with 3 disks that it's, I was sort of ad hoc explaining why the index was for each one. And so to come up with a good definition that always works seems tricky.
2 kinds of disks. There are those that are touching the box and therefore have a fundamental restriction in their movement, and there are those that are not touching the box. Mm-hmm. And do you consider that in the analysis?
I don't. And so one thing is, are they touching? So this one actually does have some freedom to move, and it's still a sort of singular point or critical point because he should have 2 degrees of freedom to move, but he only has 1 and moves in the middle. But if you go back to the, I think I can go forward to a picture of 5 disks or 4 disks. So here, that one's in the middle, but I'm not sure if I see any essential difference between that guy in the middle and the 4 that are on the outside. You do have to actually treat them a little bit differently when you try to prove things with the min-type Morse theory. So you write down some equations, and there's one equation about these 2 guys are at a certain distance. One thing to look at that's interesting. I unfortunately don't have a picture of. Is just the tangency graph. So this guy's connected to that and to that and to that and to that. but then you also have he's touching two sides, and he's touching two sides. And so that sort of has the structure of a graph, and that graph actually encodes a lot. And if you know that graph, you might know what's the index of the critical point. But the funny thing about that graph, and maybe this is what you're getting at, is that these guys out on the boundary are not really vertices of the graph. They're just sort of ghost vertices because they don't move. There's no disk sitting there or there. So I think of this guy having degree 3 because he's got 3 contacts, 2 with the sides and 1 with that. So basically I think of that as a graph, except I just ignore the boundary vertices. So there is something a little bit delicate on the boundary. Also, all this changes completely if we change the shape of the boundary. If we look at a triangle or a circle instead of a square, we would get a completely different list of critical points. But my feeling is it's still fun to work out small examples because they might illuminate the path to a theory. But also, my expectation would be, though, that, and I think most statistical mechanics people would guess that if you're letting the number of disks go to infinity, the shape of the boundary shouldn't matter because most of the disks are interior and the boundary ones. So when they do these Monte Carlo simulations to sample a point from this space and to measure statistics on it, they often do things on the torus. And I think they feel like that reduces the size of finite size effects. Maybe they can measure that it does. So they do it in a square, but then they just say this is glued to this and this is glued to this. So the disks can kind of go through. And so then they don't actually have, because I think if you have 100,000 disks and they start getting pretty dense, you can actually see them, some stick in the corner, and then that effect from the corner just kind of propagates out from the corner, through a significant size of the square. And that's not what they're trying to measure. So. Okay.
Actually, my question is a little bit more fundamental than before I get to the other questions. So I'll ask that one first. So you use the distance function. Basically, you smoothed your original Morse function, or the approximation, that is, being Morse. And one thing that wasn't very obvious to me is when you take a distance function, of course, distance function, when you add them, it's not a closed, it's not a closed operation on the space of distances, right? But you didn't take the sum. You actually took 1 over the distance. So how does that change how does it change the topology of your space of distances?
Right. Yeah, you're calling me on a good thing. This is actually a subtle thing, a detail that I hoped nobody would call me on. But I start with this function, and then I said the configuration space is the super level sets of this. It's like F inverse from R to infinity, everything above a certain point. But I'm used to doing Morse theory with sub-level sets, and it's also convenient. And it's also, so I could just say, then instead of looking at the super level sets of this, I could look at the sub-level sets of 1 over this, and those would be the same. Because 1 over x will just reverse the, if x is less than y, then 1 over x is greater than 1 over y. So that's order reversing transformation, 1 over x. And so first of all, I did that because I like to work with sub-level sets instead of super-level sets. The other reason is because now it's sort of like, what I really want is the max then of all these things, but that's an L infinity norm, and that's not smooth. So instead of L infinity norm, I'll take the L 50 norm or something as an approximation of the L infinity norm, because that's smooth. So the 1 over was really just to get from super level to sub level, and then also to recognize, now that I have a max is fits better in the picture of norms than min does, because it's the L infinity norm.